So today I'm going to be talking about, this is basically a follow-up from last SC's exhibitor forum. So if anyone was able to attend that and listen about, ActiveStor Ultra, which we were releasing at that time, this basically is a retrospective. This looks at our 20 years of file system experience, what's led us to develop ActiveStor Ultra and the new Panasas, what lessons we learned and how we applied them there. So what is an OSD, which is the nature of this talk and the core, fundamental part of our file system? So the OSD is basically our data storage targets in Panasas. If it needs to persist, if it's a file, if it's a directory, it's attributes, it has to live on the OSD. Everything lives there. It's also our most numerous component. So making sure the OSD is fast is how we make Panasas fast. It's also really simple, from the outside at least. And that allows us to write complex parallel file system algorithms around the OSD. We have one side that allows iSCSI access for data and attributes, and the other side for RPC management. It's also our atomic unit within our failure domain. So within a blade set, if you lose a hard drive, you lose an OSD, and that allows us to do very intelligent reconstruction around that concept. And finally, the OSD has an internal file system that's copy on write and provides powerful snapshotting capabilities. So why care? It's just a storage target. The secret sauce is in Panasas. Why spend a bunch of time developing and trying to improve on our object storage device? So first of all, as I mentioned, we can only go as fast as our OSDs go. And so it's really our speed of light. And as a result, we bury a lot of smarts inside of there to basically track and process interwoven tasks that come down through the iSCSI layer. Make sure that if you have a write and a create and a following write, those are tracked together so that we can do smart things like put the small writes onto SSD or the large writes on the hard drives. We also prioritize foreground over background access so that if you have active capacity balancing going on between the OSDs or reconstruction, we can make sure it's not slowing down your foreground I/O. Snapshots and copy on write. I alluded to this, but basically any parallel file system worth its snuff has some kind of snapshots that don't result in complete copies of your files every time you take a snapshot. You're just going to waste a ton of capacity if you don't have this feature. It's extremely hard to support though, especially if, like us, you make a demand that it can't slow down foreground access by taking more snapshots. And importantly, rebuilds have to understand how this copy on write has been applied within the OSD in order to make sure that when we rebuild all those files and all their snapshots appropriately. Internal and transparent tiering. This has been something that's been within our product since day one, and we've just added tiers as we went. Back 8 years ago, we had 2 tiers, battery-backed RAM and hard drive. We added another tier with SATA SSD in 2012. Then we added on to that with Ultra, going from 3 tiers to 5 tiers, adding NVDIMM and NVMe SSD, where we place all of our metadata in a database. We're constantly improving within the OSD. So there's a bunch of background daemon-based tasks that do everything from defrag to make sure our file system's performing well, optimizations for different components as they change in size over time, whether large files become small or vice versa. We want to move it to the media that makes sense. Consistency and coherency. People talk about parallel file systems and consistency and coherency at a high level frequently, but we don't talk about it within the object storage devices very much because it's something that's hidden from the rest of the system. But nevertheless, we still care about it. If we move something from one tier to another, while we're in flight, we have to make sure that if a write comes in for that, it goes to the right place and that we perform the appropriate locking without degrading performance to make sure we keep that. And finally, complex inside, simple outside. As I mentioned, to have a great parallel file system, they have to have a simple individual unit of storage, our OSD, in order to be fast and in order to write complex code without a ton of bugs at a higher level. So we just have our iSCSI and our RPC interfaces, but we keep all of the secret sauce inside the OSD so that we can move quickly and without bugs. So for people that are familiar with Panasas, this is our classic OSD hardware. It's a bespoke blade-based design, 11 OSDs per 4U, and customers love the easy slide-in, slide-out replacement. It has integrated 10 gig e-switching, redundant power supplies, fans, switches, custom battery backup, and allows our OSDs to basically gracefully come down if we do lose power. And this allows us to use our RAM really aggressively for write-back caching, which a lot of people don't offer. On a per OSD basis, 2 hard drives, 1 SATA, dual 1 gig E, and 32 gigabytes of RAM. There's a lot of smarts buried behind, buried with all that storage. This isn't just a giant JBOD with one CPU to do all the legwork for all those drives. And finally, as we've gone through every release over these 20 years, we've provided incremental changes. And that has allowed us to add more RAM, change the CPU, respin this custom motherboard, or slightly change the form factor. But generally, it really hasn't, the numbers haven't changed. We've always been 2 hard drives and an SSD. So what do we learn from those 20 years? What are the lessons and what are the problems that we were trying to solve as a result? So first of all, the platform, the physical incarnation of our OSD. They love, all the customers we have today and people we talk with love the installation and replacement. It's extremely modular. If you have a failure, it's a 10-second to 30-second task. This isn't like, there's no screwdrivers involved. You're not taking anything apart. But we wanted to solve the slow, expensive, and bespoke hardware design. When we started, there was nothing available in the COTS arena, and even in 2010, that made sense for PanFS. There are today, and we looked through a number of them to find the right one, which you see here with ActiveStor Ultra. Battery-backed RAM. We and our customers love the write-back and coalescing performance advantages of battery-backed RAM. If you have to sync to disk, you will be slow. There will come workloads that slow down your entire file system as a result. But that required a lead-acid battery, and these are not so nice in terms of being green. So we wanted to find the right device that would allow us to keep the pluses but ditch that negative, and that came in the form of NVDIMM. We use that for our intent and transaction logs. I'll talk about that in a second. FreeBSD integration. We still run FreeBSD on our ActiveStor directors, and it's still an amazing operating system for us. But as we looked around, we saw that Linux was offering a lot more and had come a long way since 2001, and we wanted to see if we could break out of the lock-in that we currently suffered from to adopt that. We didn't want to get rid of our appliance-grade hardware monitoring, which allows people to know everything from, hey, your smart statistics have changed on that specific hard drive over the course of a week, and it's exceeded the thresholds we deem acceptable for our hard drives. We track ECC errors, thermal temperature within the OSDs, a variety of these things. So we didn't want to lose any of that, and so we built an entire OS and platform abstraction layer to make sure that we can operate with any, even if we move from what we run in ActiveStor Ultra, OpenSUSE, if we move from 15 to 15.1 or the next version, we can do that quickly and effectively without losing any of the monitoring goods. And finally on this slide, hard drives. They're a sensible dollar per terabyte. Anybody telling you hard drives are dead is trying to sell you something or frankly doesn't have much to store. They offer a credible bandwidth and an awesome dollar per terabyte, but they have a much lower performance per terabyte than they did in 2005, roughly 80 times to get at that same amount of data inside the hard drive. So we need to add more tiers to basically deal with that problem that we were facing with hard drives. We did that in the form of the NVDIMM and the NVMe SSD. 4 more lessons. So the OSD file system, I talked about copy on write and snapshots. It's an amazing feature, something we spent a ton of engineering time to get right and to make sure it performs well. However, there are real maintenance and improvement costs that come along with every release, trying to figure out, hey, can we change our snapshots to take more of them or be a little more performant? It can be quite trying to stay up to date or even to make other changes in the system that impact that. Like COTS, finally, free and open source software came about and has reached a sufficient level of stability in Linux in particular that we felt we could adopt one and use their copy on write and snapshotting functionality and be able to get out of the business of maintaining the local file system. Kernel space OSD stack. So this was something in 2001 in particular, you kind of had to be in kernel to be fast. That's not the case today. And in fact, it's really hard for new engineers and even existing engineers to stay up to date and do serious debugging and development in the kernel. So we looked at this and we said, how can we be smart about keeping just what we need in kernel, the free and open source file system we have adopted, but keep everything else out of kernel so that not only can we develop faster, but if we run into a bug on the OSD, it's not crashing the entire thing. So we basically moved everything to user space, and that has proven incredibly useful for us. We have not seen any slowdowns relative to what we were shooting for when we tested this in kernel. small file directories on SSDs. So in 2012, we were one of the earliest ones to be smart about leveraging SSDs, not just as like a LRU cache or something, but really trying to say what parts of our file system need to be on the SSD. We did that in the form of just small files and directories, since tree walks in particular suffer from latency and seeking all over the disk. And so that was a great improvement, but we did it in a method that was a little too static. And a lot of our competitors do it exactly this way and suffer from the same drawbacks. So with ActiveStor Ultra, what we said is we need to do this dynamically. How do we look at what small is and change that over time as your file system grows and even your file types and file size distributions change? And finally, the small OSD. So this goes back to the first point, the lesson we learned about our platform. That was a fantastic, slide in, slide out kind of replacement and a nice unit of failure, but we weren't able to amortize the costs relating to our CPU and RAM and the other components of a file system over enough drives to really reach the kind of sweet point in the terabytes per dollar kind of curve that we were shooting for. So we didn't go to the full JBOD like a lot of people do, because you'd throw out too much performance and you're not able to take advantage of a lot of the smarts we built into the file system over time. So what we found is 6 to 8 hard drives per OSD was that magic number, and we'll evaluate this over time because we're able to move platforms faster. But for right now, and in the ActiveStor Ultra, that was the sweet spot. So this is what our hardware looks like inside. So you can see the outside over here, but inside, we've partnered with Supermicro to deliver this platform totally commodity off the shelf. We've made no changes to it besides selecting the individual components that they put into it. You can see we have one CPU populated, 6 hard drives in the front, SATA SSD in the back, NVMe M2 SSD for our metadata, and NVDIMM. We still maintain redundant PSUs, so you don't go down, redundant ports, so you can attach different switches, and 25 gig E per OSD, which is a huge performance jump over our past platform. I see this as the first platform in a product line. With the changes we've made to abstract away the OS and the platform, we're able to basically move with the market instead of really having to do a ton of legwork with bespoke hardware design. So it's an exciting first step for Panasas. In conclusion, we looked back on 20 years and we said we have all these lessons. We've been one of the most pervasive players in the file system space where we've seen many stars rise and fall. How do we learn from those lessons and apply them in the new product? We saw new media types that we had to take advantage of, and finally COTS hardware that made sense for us. We finally saw open source software that also allowed us to move engineering cycles away from just small components of our individual parts of our file system to the real things we deliver value on, which is parallel file system algorithms. So what it means for Panasas and our customers is portability, moving with the market, staying up to date, whether that's a platform or an operating system. COTS, adopting commodity off-the-shelf hardware so that we can go from 25 gig E to 50 gig E to 100 gig E if we're talking NICs, or brand new devices as they come out. Tiering and density has increased tremendously with Ultra, especially in the tiering realm, and we're going to continue looking and seeing if increased tiers or different kinds of tiers make sense for our customer workloads. We split up metadata from data and really see that as one of the novel software changes in Ultra, to say, okay, we're going to take metadata, put it in a database, and put that on NVMe, so you're not interrupting sequential workloads while they can just go to the SATA SSDs and the hard drives. And finally, time. We freed up time for engineers to really double down on delivering additional value for our customers. Thanks, and I'll take any questions at this time. Thanks.